Hello and welcome to this class of Industrial Inorganic Chemistry, where we are talking about the different peroxo compounds starting from your hydrogen peroxide. And as we have seen that these are very reactive oxygen species. In our biological world also, when we have O2 only, and if it gets one electron transfer to that O2 molecule, we get superoxide, followed by another electron transfer also gives you the peroxide system. So, industrially preparation of these peroxides are also very important, and today we just finished that particular part by knowing how we can synthesize alkali peroxo disulfate. So, this peroxo disulfate is a very simple one compared to that of your hydrogen peroxide and sodium peroxide or any other peroxide species like barium peroxide. This can also be electrochemically produced. Earlier we have seen the different techniques for making hydrogen peroxide and also their corresponding different salts like sodium peroxide or potassium peroxide. So, in this particular case, how we do that? We simply go for electrochemical oxidation from solutions of sulfuric acid and ammonium sulfate on platinum electrodes. So, electrochemical production of this basically giving rise to the reaction of ammonium sulfate, 1:1 reaction between ammonium sulfate and H2SO4, giving you diammonium persulfate or diammonium peroxo disulfate formation. That means, we are basically introducing the peroxo linkage between the two similar fragments of SO3. That we will see afterwards also that how you can have this. So, one hand you can have the SO3 unit and other hand you can have another SO3 unit, and in between you have the O linkage. So, that basically gives us the production of ammonium peroxo disulfate or ammonium persulfate. And for this particular case also, the voltage window for this is 5 to 7 volt, because theoretically we can use it to 2.1 volt, but for over voltage we have to cross that particular limit and we can go up to 5 to 7 volt, and with a current density between 0.5 to 1 ampere per centimeter square is useful for this production. So, based on these electrochemical parameters for say certain type of electrochemical transformation that we know simply for different types of oxidation or reduction reactions by using a constant potential coulometric oxidation or coulometric reduction. Here also we fix the potential and the corresponding amount of current which will be passed through the reaction medium or the electrochemical cell also can be controlled. So, this basically gives us some idea that how quickly we can get the production of that alkali peroxo disulfate, because this is a very neat and clean reaction, because only product we can have, because hydrogen is also produced there. And what are the types of electrodes we can use for this particular purpose? So, graphite or lead cathodes we can use for reduction and platinum for the oxidation. So, platinum anodes and graphite and lead cathodes are very much useful for the production of a very important, industrially important material based on peroxides, because we will see also the production of these important peroxide compounds are very useful, and we will also see what are the areas where we can use those material for our other purpose. So, from that ammonium disulfate or ammonium peroxo disulfate, if we want to make the corresponding potassium and sodium salt, how we can do that? Because by making this from electrochemical oxidation, we have to go for the corresponding substitution of these ammonium ions by potassium ions and ammonium ions again by sodium ions for the production of that particular potassium disulfate and sodium disulfate. So, for these particular reactions we simply go for wet chemical synthesis, and that particular reaction is known as the metathesis reaction. So, in that particular metathesis reaction, what we can use is that the same diammonium peroxide disulfate is used, and which can be substituted, that means the cation metathetic reaction or cation metathesis can be achieved by use of, instead of giving one other potassium salt like potassium chloride or potassium nitrate, we have to use something which is common, having some common anion to the potassium ion, that means the potassium bisulfate salt. So, potassium bisulfate salt producing your K2H2O8 and the corresponding other part will be ammonium bisulfate formation. Similarly, in case of this particular sodium disulfate preparation, industrially important sodium salt, because sometimes we can see we cannot use the corresponding potassium salt, we have to use the corresponding sodium salt because of your some other reactivity pattern or solubility pattern, as well as some other introduction of the corresponding ions. So, the alkaline medium, so medium is highly alkaline with respect to sodium hydroxide, and with respect to that sodium hydroxide, what we can use, that the same ammonium disulfate metathetically now produce Na2H2O8 with the liberation of ammonia now and water. Basically, what we are having in the medium is the corresponding ammonium hydroxide. So, these particular things, that means the preparation from your any sodium or potassium salt or peroxide like that of your hydrogen peroxide also, and disulfate. Now, we will see what are their uses basically in terms of their applications. So, these applications what we will see now is that different peroxides. So, we have peroxides in our hand and uses as well as applications, what we can see for them. So, what we can get, that if we have any substrate like allyl alcohol, and if we go for the corresponding oxidation of these by simple hydrogen peroxide. So, hydrogen peroxide can oxidize these to the production of glycerin. So, the glycerin production will be dependent on your this particular thing, that where we can have this formation of this glycerin. So, this allyl alcohol can be oxidized by hydrogen peroxide. Similarly, if we can have some reaction where the epoxy compounds, we know that the epoxy resins are there. So, epoxy compounds can be prepared very easily with the use of this reaction from your sodium peroxide or hydrogen peroxide. So, another alternative chemical which can be industrially prepared in a large amount is your sodium peroxide. So, making this epoxide compound is one of them is your epoxy soya oil, which is epoxy soya oil. That oil, instead of hydrogenated, you can go for the corresponding epoxide formation. So, this epoxide soya oil is useful for plasticizer for making polyvinyl chloride. So, one of the important thing is that we can use this for as a plasticizing material for PVC production. Then we can use this particular one, that means whether we can have this H2O2 or NO2O2, we get this for. So, we can have the epoxidation of the typical soya oil for making some plasticizer. So, if we can have this organic peroxide, so organic peroxides what we can get, that organic peroxides, we can make it, such as examples are plenty. One such is methyl ethyl ketone peroxide, methyl ethyl ketone peroxide, or we can have the second one as the dibenzoyl peroxide. Because these are very important compounds from industrial point of view as well as for the laboratory purpose. We can use these as very good free radical initiators in polymerization. So, both these organic peroxides are very useful for our free radical generation, which can initiate some polymerization reactions. So, free radical initiators in polymerization reactions. So, in all these cases, what we can have that if we just use to get this reaction on benzoyl chloride, this benzoyl chloride when reacts with sodium peroxide Na2O2, we get basically this dibenzoyl peroxide. So, this dibenzoyl peroxide formation from there is also very useful, which gives us O, O, O. So, this peroxo linkage can be introduced within this molecule such that which can be a typical organic derivative of your hydrogen peroxide or sodium peroxide. In a similar fashion, we can also use this example, the third example. The third example is useful in terms of the production of corresponding amine oxides, because amine oxides are very useful. So, if we can have amine function like R, if R is methyl or R is ethyl, we can have the trimethyl or triethylamine, and if we get this as oxide, which can also be sometimes very much useful material. So, the production of these amine oxides are also dependent on the availability of other peroxo compounds in large scale. So, one such example is the preparation of your LDAO, which is nothing but lauryl dimethyl amine oxide. So, formation of these which has a linear chain of C12. So, this linear chain of C12, so is a long chain, so is a lauryl group C12, and which is attached to this particular nitrogen having two methyl groups attached to it. So, dimethyl lauryl function, and then this nitrogen like that of your N oxide formation, or you have a charge separation, nitrogen having positive charge and oxygen as a negative charge. So, this has some very useful application for this preparation of making this amine oxide, because these are antimicrobial surfactants. So, antimicrobial surfactant. Where we use this? We use them in the typical dishwashers. So, where this particular one is the final rinsing agent in our dishwashers. Nowadays we use very much these dishwashers. So, the antimicrobial surfactant which have some protection on E. coli or other bacteria and which gives rise to some detergent type of activity. So, it is a special class of detergent making which is also dependent on our use of this particular inoxide formation. So, what we get therefore, that in this particular case we get this as other applications like that of your paper production or water purification. In case of water purification as well as paper production, we use them very much, because the H2O2 consumption will be dependent for purification of that particular water, and we can have the corresponding water purification because we can treat that also the effluent of the water. So, we can use them as for the treatment of effluents. So, what we can use the treatment of effluents, because this particular one, that H2O2 is the typical oxidizing agents and which can oxidize all these things. So, during this effluent treatment we can use the hydrogen peroxide for removal of phenols that means the oxidation of the phenols which can be achieved, further oxidation of the phenol which can be achieved with the use of hydrogen peroxides, then removal of cyanides through cyanate formation and the sulfur compounds like H2S, etc. That means all different types of sulfur compounds, and if they are converted to sulfur dioxide through this mechanism. So, these contamination from H2S or any other sulfur compounds can be removed. And during the production of this paper, so we can achieve this for making high quality papers production. Also we can use them for textile industry, in that cases the textile industry can have the cotton or wool they use, and those can be treated for bleaching. So, bleaching action of these peroxides can also be useful when we use these in the textile industry. Now, we will see how we can use the typical alkali peroxo disulfates. So, just now we have seen that the preparation of these alkali peroxo disulfates. So, alkali peroxo disulfates, they are used in making all the different types of reactions, particularly they are using for polymerization initiators. How they can do? So, this alkali peroxo disulfate, just now what we have seen, that is H3S having one peroxy linkage, then SO3 with a 2 negative charge, overall 2 negative charge on the species, which can go for your typical sulfate based free radical production. So, SO4 dot minus. So, this can be useful for your polymerization initiators for the production of our polyacrylonitrile. So, they can be used for making polyacrylonitrile, useful for making polyacrylonitrile. Then emulsion polymerized PVC, and then lastly etching reaction, etching of printed circuit boards in electronics industry. So, etching of PVCs in the printed circuit boards in electronic industry can be achieved because we know that these printed circuit boards has copper deposition, the copper metallic deposition on it. So, etching of those copper in the printed circuit boards can be achieved through the use of these alkali peroxo disulfates. So, what we can see now is that this particular one for the formation of these. Now, we just move on to the other species, what are our nitrogen and nitrogen based compounds. So, these nitrogen based compounds when we talk about is the first one what we will be talking in this particular segment of the class is the typical ammonia. What we all know that the production of ammonia is always a real challenging task to an inorganic chemist, because it is the most important primary inorganic compound. 80% of the worldwide production is utilized in the manufacture of synthetic fertilizers. So, inorganic chemical based fertilizer which can be produced based on the production of large amount of ammonia in the system. So, this ammonia production, because the biochemically as we all know it can be fixed from the air, nitrogen from the air, that we have seen our previous classes, we have discussed also little bit in our previous classes. But for making synthetic fertilizer, while we are talking about the production of hydrogen, H2 formation or H2 production, that H2 if we can utilize that particular H2 for the reaction with the N2 available in air, we get the corresponding formation of ammonia through Haber's process. So, for making this for the synthetic fertilizers, what we can use, that we have to use this particular nitrogen as well as hydrogen for making ammonia. And for industrial point of view, we should have a large scale ammonia production plants in throughout the world. We know that there are numerous large scale such production plants producing a total of a data of around 2010 tells us that a total amount of 131 million tons of nitrogen can be consumed or can be utilized for the production of equivalent amount which is equal to 159 million tons of ammonia. So, that is a very good achievement, that how we can utilize the nitrogen. So, nitrogen is required for your fertilizer, nitrogen is required for our protein molecules, and nitrogen is required for our food material also. But it is not so easy task for us to get those nitrogen molecules from air to be fixed in fertilizer or in food material or in some proteins. So, making this ammonia particularly a useful task for this particular case where we can have this industrial production. So, the modern ammonia producing plants basically first converts the natural gas, that is methane. We have seen that we can have the coal bed methane also. So, methane, from that particular methane we have to extract the corresponding amount of hydrogen, and that hydrogen can be utilized for its reaction with the nitrogen. So, natural gas, LPG, petroleum naphtha can be utilized for the production of large amount of hydrogen, that we have seen also in case of hydrogen production. So, this hydrogen then combined with nitrogen producing ammonia via the Haber-Bosch process, and is basically a reaction condition can be set up from optimizing so many parameters, is that at 150 to 250 atmospheric pressure and between 400 to 500 degrees centigrade, the two gases, both of them are ideally inert one. That combination of nitrogen and hydrogen, how we can utilize this particular reaction, which is not so easily achieved, where biochemically the nitrogenases can do that particular one very easily at room temperature or at atmospheric temperature or atmospheric pressure. But here we use a more drastic condition for achieve that particular conversion, where we can have 4 beds of catalysts. So, catalysts are very useful for this particular case for conversion of these particular gaseous reactions, with cooling between each pass to maintain a reasonable equilibrium constant, such that equilibrium constant should be favorable, such that large amount of ammonia can be produced and the conversion rate is also should be very high. But in some cases, in each pass only about 15% conversion can be achieved, and what we can have, the unreacted gases, the two gases, the unreacted nitrogen and the hydrogen gases can be recycled. So, the mechanism for recycling process should also be there for the industrial production of ammonia, and if we go for the stepwise this business for the 4 beds of catalyst, utilization of 4 beds of catalyst as well as the recycling process, and that particular recycling process will be very useful, such that in a stepwise manner ultimately a very high conversion rate can be achieved, which we can see from here now from our transparency, that is 97% of that particular conversion can be achieved. But thing is that the major source of hydrogen, what we are achieving it is from the natural gas, and catalyst itself requires a temperature of at least 400 degrees centigrade, because below this particular temperature the reaction is not very much favorable, and the high pressure of these two gases also favors the forward reaction. That is why we are utilizing a pressure of 150 to 250 bar, which basically alters the equilibrium towards the right hand side, towards the product side, which can give a profitable yield, because the energy consumption, the prices of those gases, the catalyst and all other manpower and all these things should be favorable, such that we can get something which is very much cost effective, because cost always play into very important role when we talk in terms of the industrial production of some material or some compound like ammonia, because these chemicals basically play a significant role to the economics of a particular country, and we can see, because we are not studying much about the thing what we can study as the corresponding chemical economics. So, the little bit of economics and the profitability of the production and the high yield of that particular conversion is always the major guiding factors for using this thing and a very high rate of conversion towards the product side. So, what are those catalysts? The most popular one and most used one is the catalyst which are basically some iron. So, based on iron, that we will see in our next class, that how these iron catalyst can be prepared, and these iron promoted, that means irons can be supported on simple potassium oxide, calcium oxide. So, several oxides like these K2O, CaO, silicon dioxide or alumina. These are basically supports which are enhancing and which are increasing the corresponding surface area of the catalyst, such that gas can come and absorbed on those surfaces and its contact for those things will be increased. So, by increasing the surface area, that means we require a supported catalyst for the reaction of all these conversion reaction between these two gases, like that of your hydrogen and nitrogen for the production of your ammonia. So, next class we will see how we utilize this particular catalyst for the production of our ammonia and other useful nitrogen compounds. Thank you very much.